Foundry giants like TSMC and Samsung Electronics producing chips for fabless companies such as Apple and Nvidia have become dominant. But there's one company that even these foundries have to rely on, that is ASML, the semiconductor equipment manufacturer. Today we'll explore how ASML became the essential supplier for the world's dominant players and how long that status will continue. Hi everyone, I'm Jay Lee. By now you're probably pretty familiar with major semiconductor companies, but if you're interested in semiconductors, there's one more company you really need to know about, ASML. By now, most people probably know that TSMC have become super subcontractors. To build advanced semiconductors, you need leading-edge processes, essentially 7 nanometers and below, and the companies that can provide these processes are pretty much just TSMC, Samsung, and Intel. These foundries might technically be subcontractors, but when it comes to making chips for big tech, they're practically in charge. Still, there's one company even they have to bow their heads to, and that's ASML. Companies are doing everything they can to get their hands on even one more ASML machine. Each one costs several $million. In fact, how many ASML machines a company owns has become a key measure of its competitiveness. So let's take a look at what kind of company ASML really is, why it's become so important, and whether the foundry companies that rely on it can ever break free from ASML's grip. First off, to understand just how important ASML is and why it became such a key player, we need to take a look at the semiconductor manufacturing process itself. Wafer fabrication, oxidation, photolithography, etching, deposition and ion implantation, metallization, EDS testing and packaging. There are 8 main steps in making a semiconductor. Let me briefly explain. The first step, wafer fabrication. This step creates the base disk, the wafer, where the chip circuits we know are etched. You could call it the essential foundation work. The oxidation process forms a thin layer of silicon oxide on the wafer's surface. You can think of it as a kind of protective shield. It not only protects the wafer from outside materials, but also helps block leakage currents between circuits inside the chip. The third step is the photolithography process. This is where the actual circuit patterns are drawn onto the wafer. Photolithography is a shortened term, but it basically means using light and a stencil-like mask to project and print patterns onto the surface. So it's like using light to stamp circuit patterns onto the wafer, kind of like printmaking. That's why it's also called the exposure process, since it involves exposing materials to light. Going into the specifics, first the oxidized wafer is coated with photoresist. That's a light-sensitive material that weakens or hardens when light hits it. You can compare this step to preparing photographic paper. A key part of this is the photomask. It acts like the stencil or film negative in this process. It's made by drawing the circuit pattern in chrome onto a quartz plate. Then, when light is shined through the mask onto the wafer, only the uncovered areas of the photoresist react, and that's how the circuit gets printed onto the wafer. After the circuit pattern is imprinted using light, the next step is etching, which removes the unwanted material. To clearly separate and protect the circuits, a thin insulating layer is added. This is the deposition step. Then comes ion implantation, where ions are injected to give the semiconductor its electrical properties. Next, metal wiring is added during metallization to connect the circuits for electrical signals. Then it undergoes the EDS process, which is basically testing before finally being assembled during the packaging stage. And that's how a semiconductor is basically made through those 8 major steps. While every stage is vital, the one generally considered the most important in the entire process is photolithography, which I described earlier. Industry sources say this one process makes up almost 60% of the total manufacturing time. Cost-wise, it's also said to account for 35%, maybe even up to 50% of the total production expenses. Essential for this stage is the exposure tool, or lithography machine. Simply put, it projects the light to pattern circuits on the wafer. While many companies make equipment, the leading producer of these vital lithography tools is ASML. ASML's share of the global lithography equipment market is overwhelming. They hold about 85% of the entire market. Japan's Nikon and Canon hold shares of around 10.3% and 4.3%. And in the EUV market needed for processes below 7 nanometers, ASML controls a full 100% share. So how did ASML become such an absolute powerhouse? Actually, first question, was ASML always this dominant player ruling the semiconductor market? The answer is no. ASML actually used to struggle against dominant Japanese competitors, much like Korean memory companies once did. Now, though, they are the undisputed leader. We'll explore how they achieved this alongside advances in lithography. Recall that I explained lithography tools use light to effectively draw the circuits onto wafers? Well, the specific light utilized for this isn't the same as the light we normally see around us. So, lithography uses light with shorter wavelengths than visible light. Specifically, it uses ultraviolet or UV light. For comparison, visible light wavelengths are about 380 to 780 nanometers, while UV light is down in the 10 to 380 nanometer range. And why use such short wavelengths? It's because the core goal of lithography is to draw the semiconductor circuit lines as thin, as narrow as possible. Drawing thinner, more precise circuits allows packing in more transistors, boosting the chip's performance. Shorter wavelengths are key for this. The shorter the wavelength, the more precise the process can be. So, companies making lithography tools continuously advanced the technology, utilizing various light sources to get shorter wavelengths. The earliest machines, commercialized in the 1980s, relied on mercury lamps as their light source. This approach is known as mid-UV, or MUV. This MUV approach utilized wavelengths in the mid-300 to mid-400 nanometer range. This allowed making chips with processes from 1200 down to 350 nanometers. When you compare that to the 3 nanometers or 2 nanometers nodes we talk about today, it doesn't sound like much. But back then, it was considered a huge innovation. Japan's Nikon and Canon reportedly held leadership in the MUV lithography market back then. This was during the 80s and 90s, the peak time for Japan's semiconductor industry. Together, their market share was over 75%. ASML started in 1984, a joint venture between Philips and ASM International, and entered the lithography field too. At the time, however, they reportedly made little impact, overshadowed by dominant Japanese companies. However, things began changing around the 2000s. As demand for circuit miniaturization kept rising, light sources also started to improve. The old mercury lamp-based MUV from the 80s and 90s gave way to deep ultraviolet, or DUV technology, which used excimer lasers as its light source. DUV technology is further split into krypton fluoride and argon fluoride. KrF provides a 248 nanometers wavelength, while ArF achieves an even shorter 193 nanometers. Using these advancements, ASML produced various lithography systems and greatly expanded its market share. This is where Nikon and Canon began to lose their edge. They started focusing more on consumer devices, particularly their profitable camera businesses, instead of lithography equipment. Because of this, they neglected lithography R&D and gradually ceded market share to ASML. Ultimately, Canon stopped making tools after KrF, Nikon after ArF. ASML, however, kept innovating. In the late 2000s, they developed ArF immersion lithography, overcoming earlier dry ArF limitations. This breakthrough proved DUV alone could enable 7 nanometer processes. So ASML, once trailing in third place behind Nikon and Canon, eventually captured over 90% of the DUV market share. But the push for finer circuits continued beyond the 7 nanometer node. As chip designs advanced, the industry demanded tools for even more precise patterning. ASML's solution, which secured its absolute leadership today, was EUV extreme ultraviolet lithography. EUV light features an extremely short 13.5 nanometer wavelength right at the UV spectrum's edge. Developing the tools to actually use this was, as you'd expect, reportedly very tough. Though its potential was clear in the early 2000s, successful commercialization only arrived nearly 20 years later. Compared to MUV or DUV, EUV's wavelength is so short it gets absorbed by nearly everything, even gases. This meant the light's energy would disappear before reaching the wafer, even if generated by the machine. Consequently, harnessing EUV was considered extremely difficult. But ASML persisted, investing heavily for over a decade despite the losses. Following a prototype EUV tool release in 2006, ASML has now become the world's only manufacturer producing commercial EUV systems. So why was ASML able to succeed with EUV development when the Japanese competitors were pulling out one by one? It probably wasn't simply a question of money. After all, giants like Nikon and Canon were actually bigger companies than ASML back when EUV development first started. Regarding this difference, veteran Japanese economist Professor Emeritus Yukio Noguchi assessed in an article that ASML succeeded because it relied on other companies for core technologies. In the high-stakes semiconductor equipment market, the claim that depending on others' tech, rather than seeking patents and monopoly, was the secret to success sounds a bit strange, doesn't it? ASML filled its need for diverse EUV machine components either by outsourcing their production or through acquiring the companies that made them. For instance, in 2013, they acquired the American light source specialist Timer. Then in 2016, aiming to boost its tech in optics like lenses, ASML secured a stake in the German optical giant Zeiss, forging a strategic partnership. Furthermore, starting back in 2012, ASML launched an EUV co-investment program with major foundry companies around the world. The program worked like this. Customers with their own fab semiconductor factories funded EUV development by investing in ASML's non-voting stock. In exchange, these investors received priority access to buy the EUV machines, fewer than 40 of which were being produced annually at the time. So companies like TSMC, Samsung and Intel lined up, investing around $5.4 billion in total. This funding helped ASML successfully develop its EUV machines. Indeed, it's often said ASML's only truly in-house tech is its software. The company actively relied on component outsourcing and external investment to develop its EUV systems. Of course, this software is certainly one of ASML's core strengths. Lithography machines need incredibly complex computation and control, often called the world's most precise equipment. Even back in the early 2000s DUV era, ASML proved its prowess with unique control software that reportedly doubled production throughput compared to rivals. Japanese firms, in contrast, stuck to their usual do-it-all-in-house development model. They aimed to build everything internally, lenses, the whole system, software too. Reportedly, only the light source chemicals came from outside. This approach ultimately failed them. By the mid-2010s, all had withdrawn from the EUV race. So ironically, the reason ASML succeeded with EUV development and came to dominate the entire market was precisely because of its open innovation approach, looking outside the company. You could argue it was a key strategic judgment that skillfully leveraged the interconnected nature of the semiconductor industry itself. ASML leverages its tech for consistent growth. Even in the 2023 chip cycle downturn, revenue grew 30%, YoY net profit rose 39.4%. Revenue reportedly hit 27.6 billion euros, about $30.4 billion. That's impressive growth from starting near a Philips dump to now surpassing Philips's revenue. ASML also recently unveiled its next-gen high-NA EUV tool, the XE5000. Reportedly double-decker bus-sized, it costs a staggering $350 million each. That's nearly double the previous NXE 3600D's cost of about $154 million. The new XE5000 tool pattern circuits 1.7 times finer than prior EUV machines. This capability is expected to make mass production possible for chips at 2 nanometers and even smaller nodes. So Intel, now pushing back into the foundry business, received the world's first high-NA machine in December 2023 and is currently beginning pilot production. Samsung Foundry also plans research using this tool at its joint R&D center with ASML, currently being established in Hwaseong, South Korea. However, let's also examine the question of just how long this dominant period for ASML can actually continue. First, there are indications EUV demand could be slowing. The past few years saw intense manufacturing competition, sparking a race to announce smaller process nodes. Even with criticism that these nodes were partly marketing, foundries heavily promoted tech like 7 nanometers, 5 nanometers, and 3 nanometers, enabled by ASML's EUV. The fabless chip design companies also emphasized which specific foundry and nanometer process was used for the chips inside their latest products. However, this overheated competition started causing problems. Adopting these cutting-edge processes somewhat recklessly led to excessively high production costs. Rushing into mass production with low yields before the technology was fully stable naturally drove up the cost per chip. Take TSMC for example. A wafer using the 5 nanometer process costs around $14,000, while a 3 nanometer wafer is estimated to cost $20,000. Looking ahead, a 2 nanometer wafer is projected to cost $30,000. As these wafer costs increase, the price of each individual chip inevitably goes up too. Since chip manufacturing costs, often the biggest part of a device's price, had nearly doubled in just a few years with process upgrades, product prices naturally rose, burdening consumers. Consequently, fabless companies, the foundry's customers, increasingly chose relatively cheaper, older process nodes over the cutting edge. This in turn naturally led to lower foundry demand for the latest EUV equipment. Indeed, ASML's new EUV orders fell sharply back in Q1 2024. Compared to Q4 2023's 5.6 billion euros orders plummeted nearly 90% to just 656 million euros. As a result, ASML's total revenue for that quarter also reportedly dropped about 27% from the previous one. So, with high costs, foundries trying to upgrade existing tools instead of buying new ones poses another major challenge for ASML. A key example is recent statements by TSMC, which owns the most ASML equipment. At an April 2024 conference, TSMC announced plans for 1.6 nanometers chip mass production in late 2026, drawing attention by saying it's possible even without ASML's newest high-NA tools. Sure, this could be seen as a strategic move against Intel, given their foundry ambitions and high-NA EUV plans. On the other hand, it could also suggest the intense competition for cutting-edge EUV machines might ease up in the future. The key technology that makes this possible is called multi-patterning. Essentially, this technique repeats the photolithography process we described earlier multiple times on the same wafer. Doing this allows finer processes to be achieved even using relatively older lithography equipment. Recall the stir when it was revealed that the Kirin 9000S chip in Huawei's Mate 60 Pro was made using a 7 nanometers process? It was surprising because EUV tools believed necessary for sub-7 nm processes are restricted from China by US sanctions, seemingly blocking such advanced chip production there. However, reports indicated the Chinese foundry SMIC actually produced it using DUV equipment along with sophisticated multi-patterning. So TSMC seems to be signaling confidence that using multi-patterning, it can break the 2 nanometers barrier even without high-NA EUV tools that cost over double the previous generation. While this likely doesn't mean TSMC will ditch ASML completely, its dependence could decrease. Also, there are moves to shift away from ASML's dominance in advanced lithography. One example is nano-imprint lithography, NIL, from Japan's Canon, previously overshadowed by ASML. Simply put, NIL isn't like current photolithography using light and masks. It's more akin to stamping. A mold with the nanoscale pattern directly imprints circuits onto the wafer. Canon claims NIL can currently handle 5 nm level processes and asserts it's close to achieving 2 nanometers production, matching EUV's reach. However, NIL's biggest potential advantage is cost. It's reportedly less complex and power-hungry than photolithography, possibly costing an order of magnitude less than ASML's EUV equipment. So, if standard ASML UV costs around $154 million, Canon's NIL tool might cost just $15.4 million, a huge difference. And indeed, some companies are already conducting process tests using NIL equipment. These include the Japanese NAND maker Kioxia and South Korea's SK Hynix. Both firms are reportedly exploring using NIL to mass-produce NAND flash memory. It seems the potential for a shift in the manufacturing paradigm might appear first in memory chips, which have a relatively simpler structure than logic processors. So, just as ASML beat Canon and Nikon with the new EUV paradigm, ASML itself is now facing challenges from newer process technologies. Of course, these new technologies won't instantly surpass ASML's or completely steal its market share overnight. For any new technology to be widely adopted, a whole ecosystem of materials, components, and related equipment needs to be built up first. But it's important to remember that even ASML, holding a monopolistic supercontractor status now, can always face new challenges. And that concludes our story on ASML for today. If you found this interesting, please subscribe and hit the like button. Thank you.